Imagine pitch-black darkness 3 miles beneath the Pacific Ocean surface. The environment here is absolutely freezing and silent, where the water exerts a crushing pressure of 600 atmospheres. That equals over 8,500 pounds per square inch. A brutal force that would instantly flatten a military submarine like a soda can. Suddenly, blinding high-power LED headlights flash open through the deep silt, revealing a 30-ton remote-controlled robotic crawler tracking slowly across the soft floor. As its massive metal claws tear raw, potato-sized battery stones straight out of the mud, it becomes clear that this is not a standard scientific voyage to study marine life. It is the front line of a trillion-dollar industrial war where global superpowers are racing secretly to claim the deep ocean plain, and the battle for survival begins with the armor of the abyss. To survive the abyssal plains, standard maritime engineering materials completely fail, as steel simply buckles under 600 bar of uniform compressive force. Engineers must rely on flawless spherical geometries to distribute the intense stress, choosing a high-grade titanium alloy as the material for manned pressure hulls. This metal possesses a high yield strength, low total density, and offers near absolute corrosion resistance inside the freezing salt water. The structural thickness of a manned capsule uses strict maritime classification rules. For a standard 2-meter wide sphere, this yields a 52mm base thickness, but real-world manufacturing requires thick margins to survive the chaotic depths. Thus, engineers forge the titanium sphere with a solid 80mm wall thickness to protect the crew from microscopic flaws and viewport stress zones. Hemispheres are fused together using a precise process called electron beam welding, and the seams are verified with a massive 7.5 mega-electron-volt X-ray radiography check. To rise back up, the vehicle cannot use traditional empty air tanks, as high pressure would crush hollow metal tanks instantly at 4,000 meters. Instead, they attach blocks of high-performance syntactic foam for passive buoyancy. This composite material is packed with millions of hollow glass microspheres, allowing the foam to retain its shape perfectly under a crushing 90 megapascals of force, while keeping water absorption below 1% during long undersea operations. The metal sphere is safely armored, but the real prize lies outside the hatch. The primary target on the ocean floor is a multi-trillion-dollar raw mineral prize consisting of millions of dark, potato-sized rocks scattered across the deep silt. Marine scientists formally call these strange geological formations polymetallic nodules, which hold an unbelievable wealth of critical industrial battery metals. Surprisingly, their million-year creation process is one of the strangest anomalies in nature, as every single nodule slowly grows around a hard, tiny central nucleus core that is often a fossilized tooth from a prehistoric shark, a tiny basalt fragment, or ancient bone debris. Metal ions dissolved in the dark ocean water slowly stick to this core through 2 completely separate chemical pathways. The first pathway is hydrogenetic growth from cold, oxygen-rich water layers, an incredibly slow process that adds just a few millimeters every million years to produce a smooth surface rich in pure iron and high-grade cobalt. The second pathway is diagenetic growth from underground sediment pore water, which happens up to 10 times faster than water column precipitation, creating a rough texture that concentrates manganese, nickel, and copper. Together, these pathways create a chemical matrix containing 4 vital industrial metals. From a macroeconomic perspective, this abyssal ore is an absolute engineering cheat code. Mines on land face rapidly declining metal ore grades over time, forcing workers to dig through massive layers of earth and create toxic mining waste that releases heavy hazardous elements like arsenic, mercury, and antimony. In contrast, these deep seabed nodules rest loosely right on top of the soft mud. They are highly porous, remarkably easy to melt down, and create zero solid waste. This clean processing profile allows for a highly efficient metallurgical flow sheet, making superpowers see these seabed stones as the ultimate shortcut for green energy. Nickel, cobalt, and manganese are vital feedstocks for high-capacity electric vehicles, forming the core chemistry of advanced nickel-manganese-cobalt (NMC) battery cathodes that run everything from consumer electric cars to advanced military equipment. For China, claiming these seabed rocks is a matter of absolute strategic survival. Beijing currently relies heavily on nickel imports from mines in Indonesia and volatile cobalt supplies from the Democratic Republic of the Congo. This massive foreign dependency creates a critical choke point for their domestic supply chains, but by securing deep-sea territories, they bypass land-based jurisdictions entirely and lock down a permanent shield against future resource embargoes. However, this aggressive resource grab has pushed the Pacific to a boiling point. The main geopolitical battlefield for this undersea wealth has clear coordinates, with superpowers clashing over a region called the Clarion-Clipperton Zone. This vast abyssal plain stretches across 6 million square kilometers of the Pacific Ocean, sitting in international waters between Hawaii and Mexico. The zone holds an estimated 21 billion tons of polymetallic nodules, containing more nickel and cobalt than all known land reserves combined. This massive concentration is regulated by an agency called the International Seabed Authority, ISA. Operating under the United Nations, they manage permits for the international seabed, but the agency is currently trapped in a fierce, multi-year regulatory deadlock. Many member nations worry about the severe environmental impacts of deep-sea mining, as heavy mining vehicles create giant sediment plumes that choke out marine life. And scientists warn that fragile, benthic ecosystems might take centuries to fully recover. This ongoing regulatory gridlock triggered a series of aggressive legal maneuvers. The tiny Pacific island nation of Nauru recently invoked a special legal clause known as the 2-year rule under international ocean law, forcing the agency to consider commercial mining applications without a finished code. To hedge against further delays, Western commercial corporations launched a new play when the metals company officially bypassed the global agency in April 2025 by filing for exploration rights directly under domestic United States mining codes. Updating its domestic codes radically speed up mining permits, directing agencies to bypass slow international regulatory channels completely. The sudden commercial rush has triggered a massive global diplomatic war. This go-it-alone strategy angered ISA member states across the globe. Superpowers like China, Russia, and France strongly condemned the American move, and that, bypassing the international framework, directly violates established maritime law. While the new ISA Secretary General warned that unilateral actions are unlawful, but the United States is not a party to the treaty, and American legal experts argue that seabed mining is a high seas freedom. This massive legal divide creates a chaotic environment for global investors, where overlapping claims could spark active naval grey zone confrontations at sea, fracturing global ocean governance forever. Meanwhile, geopolitical alliances across the Pacific are shifting rapidly toward Asia. In early 2025, the island nation of Kiribati tore up its Western partnerships and began exploring lucrative bilateral mineral deals with state-backed Chinese enterprises instead. China has carefully positioned its own organizations to dominate this space legally, utilizing state-run giants like Comra and China Minmetals to handle their oceanic exploration operations. Together, these Chinese entities hold 5 of the 31 exploration contracts, representing the largest share of deep-sea mining territory held by any single nation. Rather than trying to break or bypass international ocean laws, they are using their immense leverage to rewrite the global mining code, ensuring the final rules favor their massive industrial machinery. Operating these heavy industrial machines on the ocean floor requires extreme mechanical engineering, especially since the abyssal plain is covered in deep, treacherous clay and soft mud sediments. This underwater soil has an incredibly low shear strength of just 5 kilopascals, meaning standard tracked vehicles face a risk of sinking under this weak surface. If a heavy crawler slips, the soft mud immediately loses its cohesive grip, causing the entire multi-million-dollar vehicle to capsize and sink straight into the earth. To solve this terrain issue, subsea crawlers are designed with ultra-low ground pressure, utilizing advanced syntactic foam modules and wide rubber tracks to spread their weight. 2 notable heavy-tracked collectors are currently leading real-world deep-sea trials. The first is Patania 2, a 35-ton underwater tracking monster that utilizes high-velocity water jets. This design lifts nodules using a fast fluid boundary layer without scraping the mud, preventing the intake of thick clay while gathering stones at extreme rates, collecting over 100 tons of rock per hour during initial Pacific tests. The second machine is Kaituo 2, built by Shanghai Jiaotong University. This heavy vehicle features an onboard drill, hydraulic collectors, and autonomous navigation, smashing records in mid-2024 by operating successfully at 4,100 meters. Once collected, the heavy rocks must travel miles straight up to the surface via a massive vertical lift system deployed from a ship. Converted drill ships like the 200-meter MV Hidden Gem run these surface extraction facilities, lowering a rigid steel riser pipe that stretches 4.5 kilometers deep to pump a fast slurry of seawater, fine mud, and rocks upward. Designing this multi-mile vertical pipe requires intense mathematical modeling, as the steel pipe behaves like a slender beam under extreme tension. It must survive severe drag forces of moving ocean currents, which can trigger dangerous vortex-induced vibrations that snap the rigid steel structure. To protect the pipe, engineers drop a heavy buffer station at the very bottom to separate excess mud and regulate the flow rate of incoming nodules. This buffer attaches to the crawling vehicle using a highly flexible underwater jumper hose, a layout that isolates the rigid steel riser pipe from the movements of the crawler and ensures the entire automated system can harvest wealth without collapsing under its weight. The multi-billion-dollar race for battery minerals hides a deep military secret, as the same advanced machinery used to mine the plain serves a dual purpose. Deep-sea surveying maps the perfect routes for nuclear-armed submarines, providing high-resolution models that allow vessels to navigate stealthily through dark oceanic trenches. Oceanographic survey ships gather vital data like water temperature and salinity layers, allowing naval forces to map out highly accurate sound speed profiles. Knowing where the thermocline layer sits allows a captain to hide from sonar, letting Chinese Type 096 and American Virginia-class submarines slip past detection grids, state-owned mapping vessels like the Xiangyang Hong 01 show an alarming pattern. Logs reveal these ships spend only 6% of their time inside mining zones, while the remaining 94% is spent crisscrossing strategic military choke points. They map the vital waters around Taiwan, Japan, and the American stronghold of Guam, regularly turning off their automatic tracking transponders to go dark while performing sweeping lawnmower patterns to map secret silent transit corridors. They also drop advanced benthic acoustic sensors into 4,000-meter abyssal chasms to register and record the unique acoustic signatures of passing warships. This raw acoustic database feeds directly into China's massive underwater Great Wall network, meaning every robotic nodule collector deployed helps perfect the battle space for undersea warfare. The abyssal plains are no longer a dark, empty, oceanic void. Instead, they form a critical, multi-trillion-dollar theater for resources and national defense. Superpowers are not conquering the chasm out of pure scientific curiosity. They are building massive, heavy automated fleets to completely dominate the 21st century. The ultimate industrial gold rush has officially moved straight into the deep abyss, and the rules of international power are being rewritten on the ocean floor.